So in this video, we turn to the existence part of the proof of theorem 6.4. And the idea is the following. So the idea is to approximate the solution, construct the solution inductively. This is a very common idea in ordinary differential equations or in partial differential equations for that matter, when dealing with nonlinear problems that involve Lipschitz continuous nonlinearities. So let's see how that works here. The idea is that I want to define a process xtn plus 1, n plus 1's level of approximation of the actual solution of my SDE in the following way, by taking x naught plus the integral from 0 to t of mu s xsn, the previous level of approximation of my solution, plus the integral from 0 to t of sigma s xsn. And the idea is that at the limit, I'm going to get a fixed point. I'm going to get a process xt that is equal to x naught plus integral from 0 to t of mu s xs ds plus integral from 0 to t of sigma s xs dbs, right? So we need to show that defining a process inductively like that makes sense, and that the process we're getting the family of approximating processes we're getting, xtn, converge to something, and then that something is indeed a solution of our equation. So that's the idea here. But how do I define that? So the first thing is that I want to create that process inductively. So the first step is to understand what happened at n equals 0. So for n equals 0, I'm first going to remark that the expectation of the integral from 0 to t of mu s x naught ds, if I look at this and I take the expectation of this squared, I can apply Cauchy-Schwarz and get, let's say for every t in a finite time interval, I'm going to have that this is controlled by t times the expectation of the integral from 0 to t of, well, mu s x naught can be controlled by k times 1 plus x naught squared. That's one of the assumption on mu, that's the size assumption, and then ds that. So this entire thing is smaller than t squared times k times 1 plus the expectation of x naught squared, which of course we know is finite because we start with an x naught in L2 of omega. So what have we got here? We've got that this integral of mu s x naught ds defines a random variable in L2 of omega. Okay, what about this part here? Is that well defined at n equal to 0? So notice that sigma s x naught squared is also smaller than k times 1 plus x naught squared. That's also one of our assumptions, and that's for every s. And this means that the process sigma goes to sigma s x naught is an H2 naught process. So this integral here is well defined in the Ito sense, and I can also conclude by Ito isometry that the expectation of the integral from 0 to t sigma s x s0, which is x0, dbs squared is controlled by the expectation of the integral from 0 to t of k 1 plus x naught squared ds, and that is also smaller than t squared times k times 1 plus expectation of x naught squared. Okay, so why is that helpful? Well, I can now define xt0 to be just constantly equal to x naught for all t, and I can define xt1 to be x naught plus the integral from 0 to t of mu s xs, or mu s x naught, which is really xs0, ds plus the integral from 0 to t of sigma s xs0 dbs. Now, both processes are continuous. Xt, well, is obviously continuous because it's constant. Xt1 is continuous because, well, this is continuous as a function of t because it's an integral of something finite in the Lebesgue sense, and this is a continuous martingale because it's an Ito integral of an H2 process. So what we have here, we have that xt1 as a function of t is a continuous process. And we also know that the supremum of a t of the expectation of xt1 squared in a finite time interval has to be smaller than what was it, t squared 1 times k times 1 plus the expectation of x naught squared. Okay, so now I want to use that as the first step of an induction argument. So I want to assume for some fixed n that there exists a process xtn which is continuous and satisfies the size assumption supremum for t between 0 and capital T of expectation of xtn square is finite, and in the meantime, well, satisfy the equation such that xtn is equal to x naught plus the integral from 0 to t of mu s x s n minus 1 ds plus the integral from 0 to t of sigma s x s n minus 1 dbs. So I want that for every, should have said j equals 0 to n, there exists a xtj continuous that satisfy this equation. Right? So I've managed to define my process inductively up to step n, and I want to know if I can go to step n plus 1 in my induction argument. And I can because you have that mu, the expectation of the integral from 0 to t of mu s x s n ds, as we've seen before, is smaller than what was it? Than t squared, capital T squared, that's for every t in 0t, times k times 1 plus the expectation of x, well, the supremum of the expectations of the xtn's squared. Right, with the exact same reasoning as what we did in the first step. And also, as we did in the first step, we have, by Ito isometry, that the expectation of 0t sigma s x s n dbs squared is smaller than the exact same quantity here. And this process, SSXSN, is in H2, right? That's how we get that through Ito isometry, but that also gives us that the Ito integral defines a continuous martingale. So if you have defined the process up to n, then what you get is you get a process here that is almost surely integrable in S, and you get a process here that is in H2. Therefore, this integral makes sense and gives you an element of L2. And this integral does make sense also and gives you an element of L2 of omega. Now, not only that, but their L2 norm is controlled by this quantity on the right, uniformly in T. So this means that xtn plus 1 equal x naught plus the integral from 0 to t of mu s x s n ds plus integral from 0 to t s sigma s xs n dbs for all t in the interval 0t, that defines a continuous process that is such that the supremum from t for t in this interval of the expectation of xtn plus 1 squared is smaller than t squared times k times 1 plus the supremum of the expectation of xtn squared over that same interval. All right, so we have inductively defined the process xtn, and at every step it is uniformly in L2, albeit with a constant that's going to grow as it increases, and it defines a continuous process. Now we need to show that this family of processes, xtn, indexed by n, has a limit, and then that this limit is the solution of DSD that we've been looking for. Okay, so to show that the sequence of processes converge, I'm going to start by proving the following thing. So that's claim 2. I'm going to prove that there exists a constant such that for all t in the interval 0 capital T, when I look at the expectation of the supremum for s between 0 and little t, of the difference of the nth level approximation with this n-1 level approximation, and look at that in L2 norm, this is controlled by the L2 norm of the integral from 0 to t of the difference xsn minus xsn minus 1 squared ds, right? And once I've proven that, I'm going to have a family of inequalities that is similar to this integral inequality relations that we have in the proof of uniqueness. And that's what we're going to exploit to show that not that the differences are 0 per se, but that the differences between xsn and xsn minus 1 go to 0 fast enough. The key thing is to prove this. That would be the analog of the proof of the inequality for GT in the uniqueness part of the proof of this theorem. So how do we prove this claim? Okay, well, we write up what xsn minus xsn minus 1 is. Oh, and sorry, I haven't done the shift correctly. This should be n plus 1 to n, controlled by the integral at the previous step, and the previous step will be between n minus 1 and n. Okay, so xsn minus xsn plus 1 minus xn, let me remind you what that is. This is the integral from 0 to t of mu s xn minus mu s xsn minus 1 ds plus the integral from 0 to t of sigma s xsn minus sigma s xsn minus 1 dbs. Now I'm going to use triangle inequality and control the mu part and the sigma part separately, as we've done before. So let's start by controlling the mu part. And I'm going to use the fact, by the way, that the supremum of a sum is smaller than the sum of the suprema. So let's control first the expectation of the supremum from s between 0 and t of the integral from 0 to t of mu s s xn minus mu s xs n minus 1 ds, and take that squared. So how do we control this? Well, we use Cauchy-Schwarz, and we use the Lipschitz regularity in the x variable of the function mu. So this gives me that this is controlled by the expectation of the sup of, using Cauchy-Schwarz, I pick up a little t, and I get the integral from 0 to t of this difference here squared, which we know is smaller than k times the difference xsn minus xsn minus 1. That's true at every point omega in my probability space, because that's just a property of the function mu and its Lipschitz continuity in the second variable. So this is what I get from the assumption, the Lipschitz continuity assumption on mu, plus Cauchy-Schwarz. Okay. Now I want to take a supremum of that over all S in 0t. Sorry, this is confusing. Supremum over all S in 0t. So I should be integrating up to S here. Sorry, that would be xt here. So I'm integrating up to S. And so let's call the variable S prime here, ds prime. I'm integrating up to S, and that's ds prime. Sure. But this is certainly controlled by t squared, or t itself, capital T itself, times the expectation of the integral from 0 to little t of xs prime n minus xs n minus 1 squared ds prime, and I've lost my k here. Okay, but that's exactly what I want for the first term, for the term with mu. So now let's treat the term with sigma. So the term with sigma is a little trickier, but it's not too bad. So I'm looking at this times an Ito integral this time. So the difference is with the Ito integral, I cannot just apply Cauchy-Schwarz. I don't have a Cauchy-Schwarz for Ito integral. But what I have for Ito integral is Ito isometry. So that's what I want to use here. I want to use an Ito isometry. But the problem is I have the supremum that I need to take care of first. I don't have an Ito isometry for the supremum of an Ito integral per se. This being said, I know that the process here is in H2. So because I'm integrating an H2 process, what I have, and again I made that mistake, that says integral up to S, and that's xs prime. Because I'm integrating an H2 process, I get a continuous martingale. So to a continuous martingale, I can apply Dubs L2 inequality. So by Dubs L2 inequality, I can control the sup of that martingale by the expectation of the integral up to the endpoint t. All right, that is the content of Dubs L2 maximal inequality for a continuous time martingale. Now I can apply Ito isometry. And Ito isometry gives me that this expectation of the integral squared is the expectation of the integral in the Lebesgue sense of the squared of the processes. All right, but ds, and this and the square is here. But now I can apply the Lipschitz assumption, and I know that this is controlled by the expectation as a constant k of the integral from 0 to t of xs n minus xs prime n minus 1 squared ds prime. That's the assumption, the Lipschitz continuity of sigma in the x variable. And that concludes the proof of claim 2. Okay, so let's rewrite what claim 2 is giving us as a integral inequality. So if I define Gn of t to be the expectation of the supremum from S between 0 and t of xs n plus 1 minus xsn, and all of that squared, what is claim 2 telling me? Claim 2 is telling me that Gn of t is smaller than some constant times the integral from 0 to t of Gn minus 1 of s ds for all t in 0, capital T, and for all n, natural number, non-zero. Okay, so I'm claiming that, so claim 2 gives that, and now this should give by induction that Gn of t is smaller than c to n tn divided by n factorials times g naught infinity, right? We proved that exactly in the same way as we did in the uniqueness part of the proof. All right, so this tends to indicate that g and t will go to 0 as n goes to infinity. As long as we know that g naught is indeed in L infinity, right? If this number here is infinite, then what I'm saying there is an empty statement. So let's check that out. So what is g0t? Let's try to control that. This is the expectation of the supremum from S between 0 and t of xs1 minus x0, and that is to say the integral from 0 to t of mu s x0 ds plus the integral from 0 to t of sigma s x0 dbs. And then we square that. And then maybe let's just raise that to the power 1/2 such that we have a L2 norm. And then we can use triangle inequality, and we can control that by the L2 norm of the supremum S0t. Let's maybe use Cauchy-Schwarz straight away in here, and we get the integral from 0 to S. I keep making that mistake, sorry about that. S prime dbs prime from 0 to S of mu s prime x naught squared ds prime. That's multiplied by capital T, and we take the L2 norm of that. That's raised to the 1/2. And then we have here plus the L2 norm of the sup S0 to t integral 0 to S sigma S prime x naught dbs prime in L2. And then once again, we're going to use Dub's L2 inequality for the part here that involves Ito integral of an H2 process. And here we're just going to more simply control things by t times the integral from 0 to t of the expectation of, let's control that by k times 1 plus x0 squared, which we can because of the assumption on the size of mu. And then for the second one, using Dub's, this time we control that by the L2 norm of the integral from 0 to t of sigma s prime x naught dbs prime. Okay, and then we apply Ito isometry, and we get here, so this is t squared k times 1 plus expectation of x naught squared, point being it's finite and independent of little t. And here we get, by Ito, we get the expectation of the integral from 0 to little t of sigma s prime x naught squared ds, and all of that is controlled by t squared k 1 plus expectation of x naught squared, plus using the same size assumption here, we get a k and a 1 plus expectation of x naught squared, and this is integrated from 0 to t, but we can control that by t. So this entire thing is controlled by t squared k plus t k times 1 plus expectation of x naught squared. I really don't care what this number is. The point is it's finite and it's independent of little t. So g0 infinity is some finite number only depending on k, capital T, and x naught. So what have we got? We've got that the expectation of the supremum of xsn plus 1 minus xsn, supremum for s between 0 and little t, and you raise that to the power 2, is smaller than some constant, let's call it m. So there exists an m such that for all t and for all n, this is controlled by m times c t to the n divided by n factorial times the sup norm of G0 infinity, which actually I can hide into my M. This is the fixed number that doesn't depend on anything else. Okay, so I have this information. So in particular, I know this goes to 0, but I know even more than that. I know that this quantities here as quantity dependent on n can be summed up in n, because this is not just going to 0, this is going to 0 very fast. So let's use that. Okay, so this estimate is going to be enough to show the existence of a limiting process that's going to be a continuous process. Now, here's how we see that. If you look at the probability that the process t goes to xtn plus 1 minus xtn, if you look at this process, and you take the sup norm on the space of continuous function on 0t, we know that xtn plus 1 and xtn are both continuous processes as functions of t. So they're both in C of 0 capital T. And if you look at the norm of that, then, well, you're going to get a sup norm. So if I look at that in the space of continuous function, yes, on 0 little t, actually. And let's take that, so let's call the variable here s. The inequality that I have above tells me that the probability of this squared being greater than, let's say, 2 to the minus n, just by Markov inequality, will be smaller than 1 upon 2 to the minus n, so 1 upon 2n times m times ctn n factorial. Right, but what is that telling me? It's telling me that by Boyle-Contelli, that the probability that the sum over all n of the sup norm of these processes, that's the sup norm, is finite. That has probability 1, right? Because it's going to be smaller than 2 to the minus n, every single one of them, except for finitely many terms. All of that almost surely. That's the consequence of Boyle-Contelli. So that is to say that there exists a set A in sigma that has probability 0, and such that outside of that set, I have that for all, let's say, capital N and capital M in N, with N greater than M, the probability that xsn minus xsm, and look at the sup norm of that process, and the sup norm of that at a point omega. So I'm not taking a probability, I'm doing it for every omega, not in A. I can guarantee that for every epsilon and for every n there exists, I should write it like that, for every epsilon there exists a capital N in n, such that for all m and m prime in n, such that m prime is greater than m is greater than n, this thing here, the sup norm, well, it's going to be smaller than the sum from n equal m to m prime of the sup norm of xs prime minus 1 n plus 1 minus xsn. And we know that this is smaller than, well, we know that this series converges. So because this series of sup norm converges, this can be made smaller than epsilon. So what have we proven here already? We've proven that this map S goes to xsn of omega for all omega not in A is Cauchy in C of 0 t. And this is literally what we've proven. So we've proven that there exists an A that has probability 0, such that outside of that A, the map S goes to xsn of omega that's a family indexed by n of function, and this is Cauchy in the sup norm, so in the norm of the Banach space C0T. But we know that this space is complete, so this has to converge. So we can now define, it's going to be our solution, xt omega equal the limit as n goes to infinity of xtn omega for all omega not in A. And then this, for every t in 0t, defines a continuous process as a uniform limit of continuous function. So xt, t goes xt, this is a continuous process. Let's write it like this. Xt has a family of random variable indexed by t in 0 capital T is thus a continuous process. Okay, now that has a very good chance to be our solution. So what do we need to show about this process to guarantee that it's the solution? Well, we need to show that if I take the supremum of a t of the expectation of xt squared, that this remains finite. That's one thing. And then the next thing I need to show is that, well, it does satisfy the equation. And then we've already proven uniqueness, so we would be done. Okay, so let's do that. So first of all, let's get the L2 control. So let's fix the t now between 0 and capital T. And let's look at the L2 norm of the xtn plus 1 minus xtn. So what can I say about that L2 norm? Well, it is an expectation. Maybe let's square that. It's the expectation of xtn plus 1 minus xtn, so it's certainly smaller than the expectation of the supremum over all s in 0t of xsn plus 1 minus xsn squared. But what is that? I mean, this is exactly what we've called Gn of capital T. Right. Now, what can I say about this? Well, I can say that this is summable in n. So now, if I look at a m and an m prime in n, I'm going to have that xtm prime minus xtm in L2 norm is smaller than the sum from n equal m to m prime minus 1, so I take m prime greater than m, of my gn capital T to the 1/2. And remember that my gn capital T is controlled by m times what? m 1/2 times the sum of c capital T to the n over 2 divided by square root of n factorial. The point being, this is a converging series. So what we get here is that xtn, now for a fixed t, as a sequence of random variable indexed by n, is Cauchy in L2 of omega. Again, L2 of omega is complete, so it must have a limit. But xtn tends to xt almost surely and converges in L2. Now, by uniqueness of limits, the limit in L2 has to be xt. So that tells me that this convergence, which we knew was an almost sure convergence, actually is also an L2 convergence in L2 of omega. Now, what does that give me? That gives me that xt, the L2 norm of that, I can pick an n such that xt omega is smaller than xt minus xtn in L2 of omega plus the norm of xtn in L2 of omega. And I can make, by picking capital N large enough, I can make this first term smaller than 1, say. And the second term is certainly smaller than the supremum over all t in 0 capital T of the L2 norm of the xtn, which we know is finite because our approximating processes were all uniformly in L2. Okay, so I have a limit, it's a continuous process, and it's uniformly in L2, and now I want to show that this is indeed a solution of the equation. So let's have a look at the first term of the equation, the term that includes the mu. So I want to look at the integral from 0 to t of mu s x s n ds and see if it converges, at least in x2 to start with, to the integral of mu s x s ds. And I'm going to look at the L2 norm of that. Now, and for a fixed t. Okay, so now what can I say? I can write that as a telescoping sum. So I can rewrite that as the sum from k equal n to infinity of the integral from 0 to t of mu s x s k plus 1 minus mu s xsk ds. All right. And this would certainly be controlled by the sum from k equal n to infinity of the integral from 0 to t of mu s xs k plus 1 minus mu s xsk. Right. That's because, I mean, mu is continuous in the x variable, I know that, and xsk tends to xs, at least almost surely. So really, if I can show that this series of these norms here are summable in k, then this will tend to 0 as n goes to infinity. So how do we see that? Well, this is the usual argument. We apply Cauchy-Schwarz. So all of that, by the way, is, t is fixed and it's the norm in L2 of omega. Gotta remember that. So let's apply Cauchy-Schwarz inside and the Lipschitz continuity of the map. So we get that this is controlled by the sum from k equal n to infinity of the expectation. Let's rewrite the L2 norm as an expectation now. The expectation of the integral from 0 to, let's control it by the integral all the way to capital T. I have used Cauchy-Schwarz, so I'm going to pick up a capital T, and then this is controlled by k times xsk plus 1 minus xsk squared ds. And we're taking the expectation of this integral, square it, and all of that is to the power 1/2. And now we remember that all of that is going to be controlled by, I forgot a 1/2 here, k 1/2, t 1/2, sum from k equal n to infinity of gk of capital T to the 1/2. And that's, again, using now the point that the gk's are summable, right? They're all controlled by a constant m times a c capital T to the k over 2 divided by square root of k factorial. And the point is that this series converges. So this goes, oh sorry, I've got a k in here, which is my constant. So I should call that L here. So this is a sum in L. And point being, this sum in L does converge. So as n goes to infinity, this goes to 0. So we have convergence of the integral of the mu s xsn to the integral of the mu s xs. Now we're going to do the same thing for the sigmas, and I think you can guess how it's going to work. The integral from 0 to t sigma s xsn ds minus the integral from 0 to t of sigma s xs itself, sorry, that's not ds, of course, that's dbs. I look at that in L2. The first thing that I do is that I apply to that the Ito isometry. I know that xs is uniformly in L2, therefore this process is H2, therefore the difference of this process and this process is in H2. So by Ito isometry, I can control that by the expectation of the integral from 0 to t, and all of that will be raised to the 1/2 of the absolute value of sigma s xsn minus sigma s xs squared ds. And now I use a telescoping series argument again, and I control all of that by the sum from L equal n to infinity of the expectation of the integral 0 to capital T even of the sigma s xs L plus 1 minus sigma s x L. And all of that is squared ds. And at the very end we take this to the power 1. We take it to the power 1/2 at this level, and we use triangle inequality. It doesn't matter because again I can use the Lipschitz continuity assumption on the sigma, and all of that will be controlled by k to the 1/2 sum L equal n to infinity expectation integral from 0 to t of xs L plus 1 minus xsl squared ds, and that is further controlled by k1/2 t1/2 sum L equal n to infinity of gl of capital T raised to the power 1/2, and we know that this goes to 0 as little n goes to infinity. So the terms in sigma also converge to what we want them to converge to. Now this is a convergence in L2 for every t. So for every t, I will be able to extract a converging subsequence that's going to converge almost surely. So what we have is that for every t in 0 t intersected q, I can find a set of measure 0, so you might as well do that from the start. Take the union from the start for a t that is rational, and there exists an A that has probability 0, such that for every rational t, what have we got? We've got that xt, and for every omega not in A, xt n plus 1 of omega tends to xt of omega as n goes to infinity. The integral from 0 to t of mu s xsn ds tends to the integral from 0 to t of mu t xtn mu s xsn ds, right? Because we've extracted a converging subsequence. So there should be a k here. K goes to infinity. So because and that's just k has been sent to infinity, and I've got mu s xs in here. So I should have said here, there exists a subsequence. And then we have convergence also almost surely. So this is at point omega, convergence almost surely of the Ito integrals. Xs and k, dbs, and then that evaluated at omega tends to the same thing with xs evaluated at omega from 0 to t. Right, so all of that to say what? All of that to say, well, every term converges to the corresponding term without an n, the non-approximated term. So the equation holds, because the equation holds, so therefore passing to the limit in the equation, the approximated equation in xt nk plus 1 is equal to the integral of mu s x s x n k ds plus the integral plus 1 plus the integral of sigma s x s n k dbs from 0 to t plus x naught. Right, so I take the limit in that, xt nk plus 1 does go to xt, and this converges to the right thing. So we have that xt is equal to x naught plus the integral from 0 to t of mu s xs ds plus the integral from 0 to t of sigma s xs dbs. That holds when? So that's at a point omega, and that holds for every omega not in A and for every t rational. But now I know that both my left-hand side and my right-hand side are defined continuous processes as a function of t. So if they agree, if two continuous functions agree on the rational, as always, they have to agree on all of the point. So throwing away maybe a set of probability 0 where this may not be continuous as a function of t, and another set where this may not be continuous as a function of t, what do we get? We get that there exists a b in sigma that has probability 0, and such that outside of that b, for all t in 0t, xt of omega is x naught of omega plus the integral from 0 to t of mu s xs of omega ds plus the integral from 0 to t of sigma s xs dbs evaluated at omega. Okay, and this equation is exactly our SDE. So this process xt is a continuous process. It's uniformly in L2, and it satisfies dxt equal mu t xt dt plus sigma t xt dbt, and at 0 it's equal to x naught. So that's it. We found a solution of our equation that is uniformly in t in L2 of omega, and that is a continuous stochastic process. And then we know that such solutions are unique from the previous step. So we have existence and uniqueness of solution processes that are continuous processes uniformly in L2. And that was the content of that final theorem in the course, theorem 6.4. Now that we have that, we really have all of the mathematical theory to rigorously talk about SDE, about the Ito integrals involved in SDE, and all the calculus that come with it. And in the next part of the course, we're going to apply that to finance and to see what all the next steps can be in taking this theory further. But now we will do that with a strong foundation, including rigorous proofs of difficult theorems, such as the one we've just seen.